Hello everyone, my name is Nachiketa and welcome back to another video. In my previous video, I had explained what a generator adversarial network was, how it works, and in this video, I'm going to show you a practical implementation of building your own GAN model in Tensorflow. So if you don't know what a GAN or a generator adversarial network is, please refer to the previous video. I'm just going to give you a small gist of it. So the GAN network is a particular form of neural networks that are designed in order to be able to create realistic looking images for most of the use cases. So it contains of a generator and a discriminator network. The job of the generator network is to take some random noise it gets and construct realistic looking images from it. The job of the discriminator is pretty basic. All it has to do, it has to take an input image and basically say that whether the given image is real or not. So the ideal goal is that when we're training this entire network, the generator becomes so good at creating real looking images from the noise that the discriminator is completely fooled and is not able to tell whether a given image is real or was it constructed by the generator. So in this video, we're gonna create a GAN model which will be able to generate realistic looking handwritten digits. For this, we will be using the famous MNIST dataset. So let's straight away dive into the code. This notebook is basically available by Tensorflow itself. It's a very common notebook, and all I'm gonna be doing is just to walk you through the code line by line to give you an idea of how the entire process of creating a GAN network works, the different kinds of steps you have to take in that. So once we have the base clear, we can move on to more advanced applications as well. So the first step is of course to import all the necessary libraries. The next step is to import and pre-process the dataset. We load the MNIST dataset and create training images and training labels out of it. So first of all, we resize the image into 28x28x1 and convert all the images into float values. Also, we normalize the image to construct it between a range of -1 to 1. This is a very common practice in all image problems that we deal in computer vision. That helps the model basically learn really well. Over here, I print the length of the dataset, which is 60,000 images. And now I'm going to be applying certain transformation or pre-processing to the dataset. So over here, I use the tf.data module, which basically takes input images over here and it creates it into a format on which you can apply various kinds of transformations very easily. So I shuffle the dataset, which means I am trying to create a random dataset. So it is not arranged in any particular order. To shuffle the dataset, we have to provide something called as a buffer, which we have mentioned over here. So it basically creates a buffer of 60,000 images and picks images one by one and arranges in a randomized order. In general, the size of the buffer size should be greater than or equal to the length of the dataset. Also, we create batches of the dataset. We create batches of 256 images each, right? So that we will be training the dataset on 256 images at a time. Now, the first step is to build the generator model. Now, we have to build the generator network and the discriminator network separately. The job of the generator is to take some random noise and it is gonna upscale the image to create the original image out of it. We use keras.sequential, which basically means that all the layers will be added one after the other in a sequence. So right now we add some fully connected layers and the input shape over here is 100. So basically it's gonna take 100 points from a random normal distribution and use it to create an original image. So all you have to note over here is that as you're moving through each layer, you have to note the shape that the image is being transformed into. So after the first layer, we use a batch normalization and leaky ReLU activation function. We use a leaky ReLU activation function just because this was mentioned in the original paper of GAN that leaky ReLU does better for the generator model. And we reshape the output and make sure that the output shape is 7x7 rows and 256 columns. So with each layer, the shape is increasing, right? So after the next layer, it becomes 7x7x128. Then it becomes 14x14x64. Finally, it should become 28 cross 28 cross 1, which is the original in image shape. You have to get it into that format. And you will notice that we are using convolutional transpose layers, because the traditional convolution layer downsample the image, but instead in this case we have to take the noise and upsample it to create the original image. So we use the convolutional transpose function for that, and rest we simply use batch normalization and leaky value activation functions, which was advised in the original paper. And assert function basically is just to check if the output shape at each layer is what we actually desired, right? So you have to make sure just to keep these output shapes in check. In the last layer of the model, you will see that we use the tan activation function because it gives an output between -1 to 1. You will remember that initially we had normalized the image into a range of -1 to 1. So it is crucial that the output of this model is also -1 to 1. Make sure not to use a sigmoid function over here, because we need the image to be in a range of -1 to 1. So I think these are the key things that you have to keep in mind over here. And once I have created the generator model, I have to create an instance of it, right? This is just the function definition. So I do that over here. So I create an instance over here, and to test the generator model, what I can do is I can create some random noise from a normal distribution. I provide the noise to the generator, and whatever the output was, I'm gonna plot that using matplotlib. So you can see this is how the initial image looks like. It took some noise and it created something, and to be honest, it looks like noise itself. So right now the generator has not learned how to construct an image because no training process has taken place. You can also print the summary of the generator model, and you can see that over here. You can see the output shape as it is varying, right? How it's upsampling to finally construct 28 cross 28 cross 1. You have to make sure that the output shape is same as the image dimension that you desire. Also notice the number of trainable parameters, which is around 2.3 million over here. When I show the discriminator, it's gonna be a much simpler model with a much lower number of parameters as well. This is because the generator has a more tough task. So we generally create a more advanced or more complex model with a higher number of parameters for it. The discriminator has a relatively easier task of classifying it into real or fake. So normally we create a simpler model for discriminator. So this is where we create the discriminator model. As you will see that this is simply two convolutional layers, which are simply taking the input image with a dimension of 28 cross 28 cross 1. So just make sure that this is correct over here, because this is gonna take the generator's output. So the generator creates a fake looking image that is being fed into the discriminator. And other parameters inside this, the number of filters, the kernel size is tunable. You can vary that. Just make sure to use the leaky value activation function. We use the dropout function over here to avoid overfitting. And that's it. This is a very basic 2-layer model. At the end, in the final layer, we have just one neuron in the output with an activation function as sigmoid. So the sigmoid neuron will just output a number between 0 to 1. 1 meaning that the given image was real, 0 meaning the given image was fake. So this is a very basic model. We have to make sure that the discriminator is simple. It should not be too advanced that it ends up overpowering the generator. So this balance between generator and discriminator is the crucial thing that you have to experiment and figure out. So over here we create an instance of the discriminator, and the input to the discriminator is the generated image which was created by the generator, and that is what we can print over here. So you can see it outputs a number between 0 to 1, 1 indicating that it's real, 0 indicating that it's fake. We can also print this summary over here, and you can see how the output shape is changing from layer to layer over here, and the number of trainable parameters is key. It's only 2 lakh or it's 0.2 million as compared to 2 million in the generator model. So this is what you have to keep in mind. Over here is another important thing to keep in mind, which is the loss functions. So you have to understand how we are calculating the loss for the generator and the discriminator, because they're going to be really different from each other. So we create a cross entropy loss, which we're going to be using because in binary classification, this is what we normally use. But for the discriminator, we will have to create a custom loss function, because during training, we will give it sometimes real images from the original MNIST dataset. Sometimes we will give it the output of the generator model. In both the cases, loss will have to be calculated differently. So whenever it was given real images from the MNIST dataset, the discriminator should have ideally predicted the output as 1 or the output as real. So in the cross entropy function over here, we have two arguments. In the right hand side, we have the actual output, and on the left hand side, we have the desired output, which we wanted. So whenever we give it the real output, which means we give it real MNIST dataset, the output should have been 1. So using tf.ones underscore like, we create a matrix of all ones, right? So we compute the loss like this whenever the image was real. When the image was fake, when I write fake underscore output, this means that this output was given to it by the generator. Whenever it was given a fake image, then the desired output should have been 0. If it was a good discriminator, it would have successfully predicted the output as 0. It would have identified that it has been given a fake image. So now we create a matrix of all zeros, and that's how we calculate the loss. So the total loss is a combination of the real loss plus the fake loss, because during training, sometimes we will give it real images from the MNIST dataset, sometimes we will give it the output from the generator. So that's how it becomes really good. So that is what we return over here. Generator is pretty basic. We again use the cross entropy function. Now whenever the generator generates any image, if it was a good generator, then it would have fooled the discriminator, and the output of the discriminator would have been 1, right? Because the discriminator is not able to distinguish. So the desired output is 1 over here. So we create a matrix of 1s. So whenever the generator generates an image, the job of the generator is to fool the discriminator into thinking it was real. So this is what is initially confusing for beginners, which I hope is clear why we have taken the loss functions in this particular format. Then we create some basic optimizers. We use the Adam optimizers for both. You can again modify the learning rate for generator and discriminator to balance it out. Again, this is something you have to experiment and figure out. Over here, we create some checkpoint directory. Basically, as the model is getting trained, the optimizers, the generator model, the discriminator model, they get saved in that particular directory that we have mentioned. So that is why we can use, we use this. This is optional, just to keep track of the training progress. Over here, again, some parameters, the total number of epochs, the dimension of the noise, which is 100 over here. Over here, we mentioned number of examples to generate and something called as seed, which you can ignore for now, but we'll use this during the testing time. So when we're testing the model, we're going to be creating 16 sample of noises to see how well the generated images look like. And we mentioned something called as seed, which is a common practice, so that whenever we create a random noise, we are able to replicate that during each time we test it. So we'll get to this part of the code when we are testing the model. Finally, we are creating a custom training loop, right? Because we have defined all our custom loss functions, we have to exactly mention in the training loop how the data is being passed from the generator to the discriminator, how we are calculating the loss and everything. But it's basic. We are using pre-built function, nothing really complex. So we use a tf function, which we have to use when we are creating a custom training loop, which makes sure that the function gets compiled according to TensorFlow. And over here we're creating one training step. So what happens in one epoch of the model? So in one epoch, it will be given certain images, right? And first we have to generate some noise. So we do that using tf.random.normal. So it takes some batch size and noise dimension. According to that, it just creates some noise which will go into the generator model. So in the training loop, we mentioned with tf.gradient tape as generated tape and tf.gradient tape as discriminated tape. So in the training loop, we have to keep track of the gradients of the loss functions and how they're changing with time, right? That is what the gradient measures. So for both the discriminator and the generator, we have to keep track of that, which we do using tf.gradient tape. It helps us measure the gradients and record it with time. So data flow is pretty simple. We give the generator some noise and it creates generated images. Now to the discriminator we give two things. One, we give it the generated images and save the final output as fake output. This denotes the output which was created by the discriminator when it was fed fake images. We also give real images to the discriminator from the MNIST dataset. We save that particular output with the variable name of real underscore output. Then we simply calculate the loss function for the generator, and we calculate the loss function for the discriminator as well. For the discriminator, we have to calculate the loss function in both cases, when we give it the real output and when we give it the fake output. Then using these loss functions, we calculate the gradients using the gradient function, where we give it the loss function as well as the trainable variables, right, which is basically the parameters of the model. So all we're doing is we're seeing when we're changing the parameters of the model, how the loss function is changing, measuring the gradient, and then optimizing that with time. So similarly, we calculate the gradient for the discriminator over here. Then we provided the optimizer, right? And this is a particular format. You don't need to spend a lot of time. Tensorflow has given this format. You have to use the apply gradient functions. You have to use the apply gradient function and you have to provide it in a zip format, the gradients and the parameters. So using the gradient, it will update the parameters. Pretty simple. So we do that for both the generator and the discriminator. So this was just what happens in one training step. Finally, we create a complete training loop where we give it the input as the data set as well as the number of epochs, and we basically run a for loop. So inside the for loop, what will happen is we record the time and we get batches of images from the data set and we provide the batch to the one training step that we had created. So the entire training step is going to take place over each batch of image that we create. Finally, some additional things which is not necessary but we are doing it, which is basically we generate the images. So for each epoch you want to see how the generator is progressing, how the generated images look better and better. So we'll define that later. So we create this function and display.clearOutput will basically after each output, whatever images were displayed clears that. And after every 15th epoch, we are gonna save the new weights optimizer variable into the checkpoint that we had created. So that's all that's happening in the training loop. We are printing the time for each epoch as well, and you can see the final epoch and what the final images look like by the generator. So this will help you do a qualitative analysis. And over here we have defined the generator function which we were using over here, which basically takes the model, which takes the epoch and test input. So test input is nothing but the seed that we had created in the code over here. The seed makes sure we create the same random noise each time you run this so that you can get similar results each time. So in this we get the predictions from the model when we give it some noise, and over here we simply create a 4x4 plot where we are displaying the predictions of the model. We multiply the model images by 127.5 because the output of the model will be in the range of -1 to 1. So we have to convert that back into the original scale which we are doing over here, and that's it. We are saving the image at each epoch as well. So now it's time finally to reap the benefits of all our hard work. We run the training loop, we give it the training data set as the input and the number of epochs. This is something we have mentioned earlier in the code. Because of the TQDM function we used over here, you get a nice looking progress bar and you can see the generated images at each epoch. Initially, it just gives some random noise which does not make any sense, but with each epoch, it is supposed to get better. So we can wait for 50 epochs, and normally this will be a slow process. So in my case, I'm using the GPU accelerator. Without this, I think it will probably might take an hour as well. So we can see that with each epoch, the pattern appears to be getting somewhat better. And I'll just pause this video over here, and when the epoch gets completed, we'll look at it. So now 50 epochs have completed, and you can see that the images that are generated look pretty real and they are vastly improved from the first epoch. All those images have been saved over here. You can see the difference between image that was created at the first epoch and how with 50 epochs it has learned to generate more realistic looking images. Finally, we use checkpoint.restore over here to restore the checkpoints to get the latest updated weights from the model. And that was all for this tutorial. In future videos, I'm gonna use GANs to create more advanced applications. So if you did like this video, do like this and subscribe to this channel because that motivates me to put out a lot more videos. And see you again in the next video.